Good afternoon. I will try to cover a couple of topics today, and one is the experiment we did to measure the Casimir interaction from 200 nanometers up to about 6 microns, and then the second one is something associated with what Fernando mentioned yesterday, our current efforts in order to try to determine the quantum friction, not by measuring the force, but just to measure the effects that quantum friction has in the population of a two-level system. First of all, I want to acknowledge collaborators and are sort of spread into different groups. Up to Fernando, the top group is associated with the first part of the talk, and the second group, Fernando, Paula, and Ludmila, are associated with the second part of the talk. And here are my postdocs and students at IUPUI, and I want to acknowledge the funding from NSF, Argonne National Lab, and Department of Energy, and also from KITP here for making this conference possible. So let's first a little bit for those of you that I have not interacted with, let me tell you a little bit of the story on how I ended up doing Casimir measurements. I actually came more from trying to determine effects associated with gravity more than Casimir. And so if you start with the field equation, with Einstein field equation, then basically you have the right part of the Einstein field equation, which is associated with matter and which produces the curvature of space-time. But we know that matter is well described by quantum, and so it should be quantum in nature. And then we have the left-hand side of the equation, which is purely classical in special relativity, and this is something that, of course, has been a concern for a lot of people, and I'm coming from that end. In particular, if you look into this tensor here in the low density, low velocity, which is my lab, this basically reduces the interaction between two-point masses, reduces to the well-known Newtonian interaction, and in some particular limits, we ask ourselves, well, what is the knowledge that we have that Newtonian interaction is valid when the separation between the two-point masses is small, and that is something that Gabriel showed also yesterday, and the ignorance is vast. So if you put the two-point masses of separation of, let's say, 10 nanometers, there could be an interaction which is 19 orders of magnitude stronger than gravity, and we don't know if that interaction is there or not. So these specific measurements that we started to do are associated with, let's call it corrections to gravity, and these corrections to gravity I will show in a minute that could come from very many different scenarios. But it is one specific correction to gravity in which the correction is IUPUI-like. For reasons I'm not going to discuss in here, I'm not sensitive with experiment that we do with corrections which are that go as 1 over r to the n power. At any rate, this was basically where and I will just show you in a minute why we started doing Casimir experiments, because as you can imagine, if you want to measure corrections to gravity between two masses at short separations, we had to put them close, and then the background will be the Casimir force. And that was my starting point. So the idea was I'll measure the Casimir's force and subtract it, and that was a big mistake. A little into the second part, I will not be talking about it now, but I think that this is very exciting, and Karsten mentioned something along this way. So one thing that is interesting is this part is quantum in nature, and so we can prepare, and we are preparing oscillators. So trapping a bead on an optical trap, cooling it down, and we cool it down by using a combination of parametric cooling, which is basically pushing the swing at the wrong time, and also change the trap as the particle move, which is basically cavity cooling. We can cool the particle 10 microkelvins and basically put it on the ground state. And then what we do is we do two-color excitation with gravity. So basically we design a density that actually has a modulation, and it is two-color excitation and with a Gaussian envelope. And then when we go through a full and we rotate this in front of this particle, and then that produces a pi pulse. And we can engineer if it is a pi pulse or pi over 2 pulse, and why not. So basically then we can mix the two states, and then we have now a mixed state of a quantum system through this classical field. And I have been bugging you on how we look for signatures on quantum nature of the interaction. I will not be talking about this one, but I think it's interesting. Another project that we have in the lab is to measure G, because many of you know G is the black sheep of fundamental constants, is known with the least precision. Not only that, it's the only constant that actually was in the code data of 2014. The precision of G was decreased just because the new measurements didn't coincide with the old measurements by a lot, by 5 sigma. So they have to actually make sigma larger in order to try to put all the measurements together. That discrepancy still persists, and we're trying to also do a measurement of G. Moving on, so as I said before, the idea was, in order to get better limits in here, the idea was to measure the Casimir interaction, and that here there is data from Umar Mohideen group, from Lamoureux, from Kapitulny's group, and from the Eötvös group. And for example, in the case of Umar and the case of Lamoureux, this is how these limits were obtained. Was a measurement of the Casimir interaction, and through that measurement of the Casimir interaction, check the agreement with the theoretical prediction, and then from the differences, if any, try to extract the limits of this phase space. So in here, the yellow part is excluded by the experiment, and the parametrization is in this is a ad hoc parametrization in this particular case, in which the strength is relative to the strength alpha of the new interaction, or the correction is compared with the gravitational interaction. And in this particular case, as it's a IUPUI interaction, this could come from gravity, directly from gravity in extra dimension, in which the extra dimensions are compact, or it could also come from, I don't know, some new interaction, some new particles out there, and in which these mediators, these Bose mediators have a mass. Yeah, then you get a IUPUI-like interaction. At any rate, the idea is then to do these experiments, and as I said before, the original idea is let's measure the Casimir interaction, know what we have to subtract, because the theory is very, very good for the interaction, know what we have to subtract it, and if there is any signal left, after we subtract everything else that we have knobs for, then we can obtain, if there is a new signature, and be very happy. The problem is, well, the problem is that we did the experiment, and what happens in here, this is similar to what Carsten showed yesterday. This is our data. So the data points are these crosses here. On top of that, there is on top of that, there is not a fit. On top of that is just using the dielectric function, which is the dielectric function of gold, except for the zero Matsubara frequency, in which the zero Matsubara frequency, so after doing the weak rotation, the zero Matsubara frequency is extrapolated, the data is extrapolated to zero frequency using a plasma prescription. So forgetting about that gold has a dissipation. If we do that, we get a very good agreement with the data. If instead we say that, we use the tabulated data, and we do the extrapolation to zero frequency using a Drude prescription, so just realizing that yes, gold has a finite conductivity at zero frequency, then we will get that curve on the top. And the error bars that you can barely see here are the 95% confidence level. So with very, very high reassurance, we can exclude just a Drude-like model to explain, to do this extrapolation. Now, that is our measurements. On the other hand, these measurements were done between a sphere and a plate. The sphere was 150 microns in size. And here you can see that the separation is in nanometers. On the other hand, Lamoureux did a measurement between 700 or 0.7 microns, 700 nanometers and a few microns. And what he found, on the other hand, is that this curve that he gets in here is actually obtained using through the prescription, if you wish to extrapolate to zero frequency. 2 points I want to make about Lamoureux measurements. In these measurements, he first had to subtract a residual electrostatic interaction that he couldn't experimentally rule out. And the other thing that was a little bit concerning at the time, and we discussed for some time, was if you look actually at 0.7 microns, the agreement with the dissipation-less model is better than Drude, just for that point, right? So there was some concern that we still have that, well, could it be that somehow there is something that we don't understand, and at short separations there is good agreement with a dissipation-less system, and then you go to larger separations and there is a better agreement with Drude. On the other hand, I want to make a statement which is sometimes confusing. These differences in here, you can understand also as an effect of the temperature. So when people say that you had to go to high separations in order to see the effects of temperature, that is true if you don't have the sensitivity. If you have the sensitivity, you can measure the effects of temperature at lower separations, which is what we did. So this is not that we are going from low equivalent for low temperatures, and since you are increasing the gap, then we are going into the thermal regime and only then being the thermal effects. But it is true that if you go to high separations, the difference between a dissipation-less and a dissipative prescription is a factor of 2. So it should, but the force is much smaller, but the relative difference is much higher. So at that point, what we decided in order to do the experiments we wanted to do was we cannot deal with this. We don't know what to subtract, right? So what we're going to start doing is start doing what we call differential measurements, in situ differential measurements. And that was the basis to obtain this curve in here, which I'm not going to go in detail now, but that taught us a lot about how to do these differential measurements. And it actually taught us a lot on how to rotate disks very, very fast. So the differential measurement, the idea of these differential measurements is the following. Suppose that you have, imagine a pizza. Then we can go to the real sample, but imagine a pizza in which you have slices of different materials. So let's say you have a slice of silicon, a slice of gold, a slice of silicon, a slice of gold. And then what I want to see, then I will bring my sphere. That sphere is glued to my microelectromechanical system, which is my sensitive transducer. And what I'm going to do, I'm now going to rotate this disk in such a way that the silicon slice goes under the sphere, then the gold slice, and the silicon slice, and the gold slice. And as you can imagine, if I do that, I haven't solved anything because I still will see the Casimir force of gold with silicon and the Casimir force with gold with gold. So what I do is I put the cheese on the pizza, is a layer of gold, thick enough that the Casimir interaction still will be between a gold-coated sphere, but the gold coating is thick enough that could be considered a solid gold sphere, interacting with this sample here that we have a slice of gold. In this particular case, I'm putting nickel because we also did experiments like that. But then there is the cheese layer, which is all gold, so the Casimir interaction is gold-gold. So we did a lot of those experiments. I want to spend a little bit of time on why do we do these rotations. What happens is that, as we all know, this is a harmonic oscillator, and in the limits of, in the limits of a small amplitude is almost a harmonic oscillator. So if you increase the amplitude, it's non-linear, as David did a long time ago. But in the limits of very small amplitudes and thermal 300 Kelvin is a harmonic oscillator, then you will say, well, you can rotate this at whatever frequency you want, and you're going to get the same sensitivity. That will be true if you have a perfect detection scheme. The problem is that the detection scheme, as you can see here, the response of the system as a function of frequency, when you go to high frequencies, this one, instead of decreasing as omega 1 over omega squared, actually becomes flat because you're measuring the background of your detection sensitivity. But it still is true that instead of doing that frequency, we just use the resonant frequency, then we still get the sensitivity of this very, very high Q harmonic oscillator. So the schemes from everything I'm going to say, I'm going to produce a signal. Whatever that signal is, when the sphere is on top of one side, so on top of the black, or on top of the yellow here, I will get a signal. When the sphere is on top of the black, it's another signal, and that will go tukutun, 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 and I will match that tukutun with the resonant frequency of the oscillator. So now what I have to do, I have to rotate my disk at the resonant frequency of the oscillator divided by the number of slices of silicon and gold that I have in my system. Yeah? So that is the basis of everything we have been doing of late. And the PIXA is a little bit different. The PIXA has regions with 50 sectors of gold silicon, all the way to 300 sectors of gold silicon. Just because we want to have in the same sample a variety of things that we could try and just analyze systematics. Most of the results I'm going to show is actually associated with the outermost ring, which has 300 sectors in the system. Now, for this particular experiment, at some point what we did, and this was because we were actually testing a little bit on getting our feet wet on the dark energy scheme, and we were trying to see if we could get any signature of chameleons and symmetrons. But the idea was, instead of what we end up doing in this experiment, what we did is we created a sample, and this sample actually was is just a silicon wafer. And in that silicon wafer, what we did is deep reactive ion etching, so we can make trenches. And these trenches, we did different sets, 20 microns deep, 50 microns deep, or 100 microns deep, which should take a long time. And in this particular case, we use these 50 microns deep trenches, and then we cover everything with gold. You might argue that the layer of gold is not going to be uniform throughout the system, so this was done by sputtering. You would be absolutely correct. But the point is that now this sphere will be on top of a region with gold, or on top of a trench in which the gold is very, very deep. It's 50 microns deep. And the Casimir interaction in that case is very, very small, and I'm going to say it's zero. For all practical purposes, it's yet way within the noise, and it's going to be zero. So a little bit of experimental details. As I said before, since we have 300 sectors, I can rotate the system at the resonant frequency divided by 300, but also I could measure harmonics of my signal. And then I could measure different harmonics. The first harmonic will be at the resonant frequency divided by 300, the second harmonic at the resonant frequency divided by 600, and so on and so forth. Now, a very, very, very long time is spent doing calibrations on the system, and so most of the time is actually spent doing calibrations on the system. We base all of our results in electrostatic calibration on the system, and since we are going to be rotating the disk, the calibration is not done in the region where it has the trenches. It's done on the region where the plate, this plate has no trenches. But we did it in stationary conditions and also while the disk was rotating, and we observed basically indistinguishable results. Now, we had a problem with our rotating system. Our rotating system is an air bearing, and this air bearing, the motor is the rotation is induced by lens effect on the system, so it's a brushless motor, if you wish. We don't know why, but once per rotation, the rotor of the system has a kick of 10 to the minus 8 radians. But in this particular case, we don't have to worry about it because we put that to coincide with one of the holes on the system. So 10 to the minus 8 radians with the geometry we have produces a change in the separation on the order of 5 nanometers, but those 5 nanometers happen over the 50 microns. So it's basically, we cannot see. And at a few positions, so most of the time we measure the first harmonic, but at a few positions we actually measure 21st harmonics on the signal. And when I say a few, 3. So here is the data. And all this data here for each one of the positions, this is extracted from the first harmonic, in which what we do at the beginning, what we do is we just model the system as it was a Heaviside function between the Casimir force when it is the sphere is over the gold region, and 0 when the sphere is outside over the trench. Using this Heaviside function, then we calculate the force. And here I'm just putting the modulus of the force. Of course, it is attractive. And there are 30 data points at all the separations. So you will see in a minute, at short separations, we can actually measure basically to 1 part in 10,000 the force. And at short separations, as before, it agrees very well with what we call this plasma prescription. A large separation between roughly 1.5 and 4 microns, I will show you in a minute that the force needs to be larger than even the force for an ideal metal. And this actually took us a very long time to understand where it could be coming from. And I think that at least we have now an understanding of where it could be coming from. And let me actually do a little bit of the analysis. One of the things for all of everybody that works in this field, what we have is we have a sharp edge going from gold to nothing, and the first thing you probably will think is, well, is there a charge accumulation in those edges that will give you an electrostatic force that you cannot get rid of? And then the question then is, well, we could analyze our signal, and then we're going to say that the force as a function of the rotation angle is going to have an expression. This is just a usual Fourier expression, in which what I define the angle phi equals 0 coincides with the transition from gold to trench, and that angle there is going to be defined to only 1 part in 10,000. And that is this delta here. At any rate, what we have in here is the different. We say, well, there could be a signal coming from the edge, and we are analyzing what the moments of that signal would be, and that is how they will enter in our expression. And as you will expect, with the description I have done, the dominant signal should be coming from the odd signs, which is in here. This is the signal we are trying to extract. But then we can use this expression to fit all the other parameters, and very quickly, just if not, I'm going to run out of time. Just to this was where mainly the analysis was mainly done by Giuseppe. This is a separation of 200 nanometers, and we can use the odd signs, the even signs, the even cosines, and the odd signs, just to extract all these different parameters and make sure that they make sense. And then we get at 200 nanometers, we get experimental force to be that, and then you can see that the orders, the moments of this potential correction in the system are much smaller than the forces that we measure. And of course, these contributions also will be separation dependent, becoming smaller as you move away from the system. So we have analyzed the noise, and I'm not getting into the details in here how these crosses are determined. But one thing that it is important to realize is that at each position we have the value of the force that we have, then the error in the position, then we have the experimental, the random and systematic error, plus an error or plus a contribution that we can only estimate, we don't measure directly, which is the contribution coming from patch potentials. And that contribution is more in one direction. It's an attractive force, so it's more in one direction than the other. So if we put everything together, so here are the data points, and again, there is a reasonably good agreement, and this is what I was talking about before. There is a discrepancy here between even the data that we measure, the position of the most of the average of the data is more attractive than even a plasma, but within the error bar, it is still agreeing with a plasma dissipation-less model. And that happens in all the range. And again, until you go to about 4.5 microns, the agreement with the dissipation model is not there. Another thing that is important to notice in here is that the calculations, this is an exact calculation. Blue and red solid curves are exact calculations done by Benjamin, Paulo, and Bert. But also you can see that until you go to significantly large separations, that the differences with PFA are very small. So we have this technique. It did allow us to measure between 0.2 and, well, with some resolution up to 6 microns. We found that the contribution of the edges is negligible, and at large separation, patch effects gives a contribution, and there is a good agreement between the plasma and, as Carsten showed yesterday, maybe also even a non-local Drude, so in which you do take into account the dissipation, but the non-local effects give these account for the difference that we observe between the data and the model. One thing that is for sure is that a local plasma model does not work. Is clear. So we have done experiments in very many different situations, in many different configurations. Umar has done similar things, and I think that by now it's clear that a local Drude model does not work. All right, in the next 15 minutes that I have, I will briefly talk about what we're trying to do now. As Fernando, changing gear completely, as Fernando said yesterday, if you move a polarizable particle in front of a dielectric, there is this frictional force that appears. And as he showed yesterday, this force is non-unitary, so it provides an extra channel of dissipation. But at the same time, if this dissipation is not too large, what you can do is you can measure that on a lifetime of the excitation of your system, there is an accumulation on the geometrical phase due to this new interaction coming from the frictional force. And he showed that we didn't, well, I didn't do any of this, but as a group, we didn't experiment with very many different combinations, but it happens that it looks like for the combinations that we investigated, which is the dielectric could be gold or silicon, and the particle could be a rubidium atom or an NB center. Of those, the best combination is n-doped silicon with NB center. And if the question is that optimal? Most likely not. I mean, most likely there are better combinations, but of these, very few, which are things that we can do in the lab, clearly an NB center with n-doped silicon seems to be working well. And what we're going to do, this is the scheme of an NB center. So the states that are going to be investigated on this NB center is the ground state, which is the m equals 0 of this state, of this triplet A state on NB center. And then you have that those are at a lower energy than the m equals plus minus 1. Then you apply a magnetic field and you split the m equals plus minus 1. And you effectively have a two-level system, which is the m equals 0 and then m equals 1. The usual stuff that you do with NB center is you pump the system that goes into this excited E3 state that also has an M0 and M equals plus minus 1. Note the change of units. In one of them, we are going to be measuring fluorescence, which the natural unit is nanometers. And in the other ones, we are going to be doing microwaves. The natural frequencies are gigahertz. But at any rate, two things to note in here. This energy and that energy is different. This state, the E3E m equals 0 decays directly radiatively with a very high probability back to the ground state. The other one actually decays to a metastable state. This has a lifetime on the order of 20 nanoseconds. This has a lifetime on the order of 300 nanoseconds. So what happens is if you keep pumping this, you end up preparing your state in the m equals 0 of the ground state. So the idea is basically to prepare the state in there. And now what we do is we know how to rotate the disk. And then we put an NB center on an AFM tip. We control the separation using more or less standard AFM techniques. And in the same system, what we do is we address and read the MV center optically just to measure the state, and then with a microwave coil just to set up what combination of the ground state and the first excited state we're going to have. And one thing that we have done is that this is this disc rotating at about 1,000 hertz. And what we have done in here, what we're plotting in here is how do we keep the separation between the tip and the plate. The plate is a 12-inch silicon disc. It's not the sample we're going to use, but I wanted to make sure that we could do it. And then what we do is we just map at low velocities what is the undulations of the wafer. This undulation of the wafer are on the order of 20 nanometers. And then what we do is we start rotating and we start moving the tip up and down to keep the separation at the same height. And that's what I'm plotting here. That separation is kept at about 3.3 nanometers with a 1 nanometer error, or about 7 nanometers also with 1 nanometer error. The thing that we can do is measure the lifetime of the excited state. This is the 3E state. And again, we can get on the order of 20 nanoseconds. We can make it, and Kanu told me yesterday we shouldn't be doing this. We can make it in a way that we can address as a single MV center in the nanodiamond. Kanu is trying to convince us that we should do supraradiant and then address them all together. And that is something that I learned here. So the idea that we had is to measure one. I don't know if that is what we're going to do, but it looks simpler to do that. And then what you do in order to measure the lifetime is you do a standard spin echo technique. So you prepare the system, you have the laser on, prepare the system on the ground state. With the microwave, apply a pi/2. Then you have dephasing in the equator of your Bloch sphere. There are effects that are going to produce dephasing. So instead of having equal population with equal phase of the ground state and the first excited, this starts dephasing. So you let it evolve for a time t, and then what you do is you apply a pi pulse. So all this, what they do is they go to the antipodes on the equator, and whatever produced the dephasing before produces a phasing now. And then you apply another pi2 pulse, and you look into what is the actual population that you got in the excited state. And then that is how you measure the actual T2, the decoherence time of your system. And the decoherence time of the system, as you can see, is actually large. It's on the order of 2.5 milliseconds. So you have a long time to actually do experiments. So we have not measured quantum friction. And we are setting up the system in order to be able to do so, but we have all the things in part. And I think that the attractive part in here, as Fernando mentioned yesterday, is that we're not planning on measuring the force. We discussed for a long time with Francesco how to better do this experiment, measuring the force, and at some time I gave up because it was an impossible experiment. So thank you for your time.
Okay, questions?
Thank you. Very nice talk, Ricardo. But how do you account for any edge effects? Do you have to worry about any edge effects when you have these trenches?
Well, yes and no. Yes, we have to keep them in mind. What happens is that for reasons that we don't fully understand, the contributions are much smaller than the contribution coming from the Casimir effect. My best guess is that the trench is not a very sharp edge. After we do all the processing and actually cover it with gold, it's a rounded edge that actually is another patch, effective patch contribution, more or less on the same order of the other ones, which is there, but is much smaller than than the Casimir interaction. And what we do is we actually characterize, if there was this edge effect, then we just characterize that edge effect with the moments of the distribution, yeah, and then we will actually get it from the measurement itself.
Okay, Jeremy. Thanks. Very nice experiments. I was wondering, you made an intriguing comment about in the range of 1.5 or so to 4 microns that the data was maybe a little bit stronger than the ideal Casimir force, but then it looked like maybe it was okay with the error bars. I was wondering if you could clarify.
Right. So if you just look into the average force that you measure without taking into account the error bars, it looks like in here, this point is below the calculation, and actually will be even below the perfect metal, if you wish. But if you take into account that the error bar is touching, then that's okay. I mean, that is what an error bar means. But it still bothers me. But it looks like, and I don't know why, and maybe we should talk a little bit more because you can characterize with also your samples doing Kelvin probe microscopy. It looks like there is a specific region in which the patch effect contribution is stronger. So that means that there is a lateral distribution of the patches that make the contribution more significant in this range of, let's say, 1.5 to 4 or so.
Yeah, thank you.
Hi, Ricardo. Very nice talk. I think the idea of the NV center is super interesting. I was just curious to understand, if you take the spinning disk and the NV center, if you apply a static magnetic field, and let's say the rotation has stopped, there's going to be a small splitting of the energy levels of the ground state corresponding to the magnetic field. But for the exact same magnetic field, if you rotate it, there's going to be some sort of magnetization induced just by your mechanical rotation. So that's going to change the splitting slightly from your original splitting. So I'm curious to understand whether those effects are included in the calculations, and do you have an idea of how you would separate that from friction?
I haven't analyzed what the contribution of the magnetic field. So the static magnetic field will induce a current in the disk, which will induce a magnetic field that will produce an extra splitting. I haven't calculated what the magnitude will be. It will be reasonable simply even to test experimentally just by changing two things. One is the velocity of rotation of the disk, and the other one is how far away the disk is from the center. So in such a way that omega remains the same, but the velocity changes. So the magnetic field should be proportional to omega square. So the induced magnetic field should be proportional to omega square, but independent of the radius. So by changing the two, we could get an estimate, experimental estimate, if you wish, of what will be the effect. But I have not done the calculation.
Okay, very nice. Happy to talk more. Thank you.
Yeah, Ricardo, thank you for your talk. I was wondering, when you have the sphere above the disk, which rotates, so for me, it's like you have a modulation in the sense of the optical properties, because sometimes you are above the goal, sometimes you have above the wall. And is it possible to observe something like a shuttling effect in this case, because you have a periodic modulation in a sense of optical properties?
I'm not sure I'm understanding. So we have the trenches on the silicon, yeah, and then the gold. Let's say this is the gold and this is the trench, but the sphere is always at the same height compared with the level of the gold. The sphere is not doing this. Is that?
Yeah, but on the disk you have different properties, right?
Correct. So that the point is that when the sphere is on top of the gold, we're measuring the Casimir interaction here. When the sphere is on top of the trench, still the Casimir interaction is there, but this distance is 50 microns plus whatever, 200 nanometers,
so you can see
or
that
6 microns.
But at the end, it is like a modulation
of the force, correct?
Yeah, and then I was wondering just if you can have something which corresponds to interaction with, let's say, one given with the goal at one given separation distance, plus something which is related to the modulation itself. I don't know if it's clear what I say, but...
I'm not completely understanding the question. What we are assuming is that the interaction between the sphere and the trench is 0. Or if you wish, what we are measuring is the difference in the interaction when the sphere is on top of the goal and when the sphere is on the trench. Now, if you estimate the Casimir interaction at 50 microns, that turns out to be very, very small. And as you can see from here, already when the separation is 8 microns, that is way within the noise of the system. So if you go furthermore to 50 microns, that force is too small for us to detect.
Ricardo, this is very nice work, and I'm inspired by some of the things you're doing. But my question is, the disk that you're rotating, do you feedback stabilize it? How do you control the separation between your probe and the rotating disk? Is this open loop, or are you doing some very high bandwidth?
At the time in which we are rotating, we do two things. It is at the time that we are rotating, we check the separation, but we don't control it. At the time that we're rotating, if we are rotating slow, we do active closed loop control just to make sure that it's working. At the time that we are rotating at the velocities that are shown here, we're actually doing interferometry between the tip and the surface, and just making sure that pattern doesn't change much than that. But we are not controlling the tip. We are just following a prescribed pattern. So we are lifting and lowering the tip with a previous measurement. So we are doing a constant height measurement in AFM, but without actually engaging the AFM with the system.
This is some kind of feed forward. You know.
Yep.
Okay.
I know. I have measured the profile.
Sure.
And then I'm assuming that when I rotated this, that profile will not change. We found that most of the cases is true. Sometimes we get some instabilities that we don't know what the reason was, and we actually have to start all over, including replacing the tip. Yeah.
These are in vacuum or in air?
This is in vacuum.
Okay, thank you.
Yes, Ricardo, question here. So the gold layers, how thick are they?
Typically 150 nanometers.
150 nanometers.
150.
Okay, so in the
that gives an attenuation of 10 to the minus 7 on the Casimir force.
Yeah, right. Okay, so I'd like to discuss with you something.
Okay.
More questions? One more question? One more? One more? I guess we're ending. So thank you, Ricardo. Great talk.